want to show you how to add up something different in this video as opposed to the last video. And as is always the case, it's something that we could start off with the general idea or a very specific idea. Now, a couple of videos ago, I had showed you this, or recall this. Here's, let's say, a 1 by 1 square, and we chopped it up like this. And you could chop it up a bunch of different ways, but if we chop it up like this, the area here was, so I already did this, so I'll just go a little bit faster on this. So 1/2, 1/4, 1/8, 1/16, so on and so forth. So we could see from this picture, just from looking at this picture, it's obvious that 1/2 plus 1/4 plus 1/8 plus 1/16 plus that equals 1, because that's the area of the whole square. Now, we have this, well, it's a sequence of numbers, and we're adding them up, and like I said, that's called a series. But this seems very specific to this picture. And it turns out that we're really going to want to be able to add up things that look like this more generally. So it doesn't have to be 1/2, 1/4, 1/8, 1/16. Well, what's really going on here generally, at least in this case right here, what we have, one way to look at it would be we have 1/2 raised to the power of 1 plus 1/2 raised to the power of 2 plus 1/2 raised to the power of 3 plus so on and so forth. Now, instead of going to infinity, which maybe you think, well, it's just too great of a leap for our first thing, let's just go up to some particular number. Let's say now I could pick n for any number, or 10 or 100. Let's just go up to, let's say, 10. Now, you could do this on a calculator. There's no doubt about it. There's no question about it. But it turns out that there's an easier way to do it, and this is, again, really important. It may seem quirky or a one-off, or this is like a puzzle, and fine, we solved the puzzle, but how could that apply to other things? It does. So it's actually worth your time to exert the effort on following this. Now, it's not really that difficult, what I'm about to do, but here's what I think of it as. I think of it as tricky. In other words, whoa, who thought to do that? I mean, once you know to do it, fine, it's great, it's easy, but who the heck came up with this? Well, I don't know. I mean, what I want to show you right now, somebody showed me. Maybe you've seen it before. Now I'm going to show you, I guess, once you know, you know. So, boy, I got to say right now, in fact, it's so tempting to do this in the following way. I'm going to do it. Look at what we've got here. We've got a number raised to the power of 1, and a number raised to the power of 2, and a number raised to the power of 3. Now, it's going to turn out, we want that to not just have to be 1/2. We're going to want to let this number in the parentheses basically be any number. In particular, we're going to want it to be a number between 0 and 1, but basically want it to be any number. And there's a standard letter choice for this, and our book uses it, and most textbooks uses it, and most people use this number, and I am too, and I'm fine with this number. And what people use is the letter R. And they use R for ratio, and a ratio is another way of expressing it. It's a fraction, it's a rational number, but that's usually what's the letter that's used. It's called the common ratio. So we've got R raised to the power of 1 plus R raised to the power of 2 plus ... all the way out to, let's say, R raised to the power of n, because it doesn't have to be added up to 10. Could be any number. And suppose we want to figure out what this sum is. So I'm going to use S for sum and sub n because we're adding up to n. Now, the way I've written this right here, that's pretty standard. It's the way our textbook writes it. It's the way most textbooks I've ever seen write it. It's the way most teachers write it. It's the way most people write it. So even though I could choose different letters, this is pretty standard letter choice. What we want to do is find an easy to use formula. This is a pain, laborious, tedious, time consuming. We want to find a relatively quick way of doing this. And I'm going to show you how. Is it difficult? No, but it really seems like a magic trick, like you pull a rabbit out of a hat, and presto, you get this great answer and you wonder, hey, how did you think to do that, or how was it done? Okay, so I'm going to show you. We'll come back to this top one. So see this top one, that's a specific example, and we can figure that out once we get this formula really easily. What I'm going to do, and again, I want to emphasize this, I'm about to do something which is easy. But I know the first time I saw it, I thought, whoa, why are you doing that? Or how did you think to do that? Even though it's easy. I'm going to multiply both sides by r. Can I do that? Yep, because I'm going to do the same thing to both sides. So let me go ahead and do that. So r times s sub n. Now, if I multiply this side by r, I don't want to make this, what I'm writing up here, too messy. If I multiply this by r, I would use the distributive rule. And you would have r times this, which is r squared. And then you would have r times this, which is r cubed. And, you know, you would keep on going. Now, what would happen up here? Maybe I should, let me write a term, an extra term in here. R to the n minus 1 on the board. Wiggle there. Plus r to the n minus 1. Now that's just one less than the final term that we're going out to. What happens if you multiply this by r? What's r times this? Here, let me do this off the side here. R times r to the n minus 1. What's our rule of exponents? Same base. There's a 1 there. Add the exponents. So r to the 1 plus n minus 1. And that's r raised to the power of n. So when this term gets multiplied by r, you wind up with an r to the n. And then when this term gets multiplied by r, we do a similar thing here. R to the n plus 1. So I multiplied both sides by r. Was that difficult? No. But it's weird in the sense that if you haven't done this before, there's no way you can know where I'm going with this. It's just like, why are you doing this? Strange. Remember in algebra, you can always do the same thing to both sides. Always. Whenever you want. You don't have to explain why you're doing it. It's an allowable maneuver. You can do it. Now, this equals this. So this side and this side, they are the same thing. They are the same thing. So what I want to do is I'm going to take this and subtract this. And then this right side and subtract this. Because these two are the same thing. What would I have on this side? I would have Sn minus r times s sub n. What happens over on this side? Well, look, this is going to cancel with that. And you know, there was an r plus 3 that would cancel with that. We're going to get almost everything to cancel out. In fact, all the way up to that canceling out with that, but this will be left over. So what do we have left? We have r raised to the power of 1 minus r to the n plus 1. Again, what I did there was essentially simple subtraction. But I think what confuses most people, aside from working through the little details here, is that why am I doing this? Where are you going with this? What is the point? Just have to put that off to the side for a minute. I want to factor out the s sub n here. And I'm going to get 1 minus r times s sub n. Okay, that's just a simple undoing of the distributive rule. I could have phrased it. I could have said add like terms. I could say factor out s sub n. You can say it a bunch of different ways, but I hope you see how that works, because that's pretty easy. And then over here, it's kind of interesting. I could mess around with this. I could factor out something, but in the next video, you'll see why. I'm just going to leave this as it is. I'm going to write this like this, r minus r to the n plus 1. Now I want to divide both sides by this term. Here's what we get. We get the formula that we've been looking for. And let me just go ahead right away and let's use it to calculate this sum up here. What does it say? Oh, look, this particular sum right here. It says to find the sum up to the 10th term, you take the common ratio, subtract the common ratio raised to, well, in this case, it would be 10 plus 1, which is 11, divided by 1 minus the common ratio. Just hang in there for a second. I know this looks but it kind of is for right now. Hang in there and you'll see that it won't be necessarily. So in this case up here, this is 1/2 minus 1/2 raised to the power of 11, because it's up to 10 plus 1, and then divided by 1/2, sorry, 1 minus 1/2. This is not very nice, I have to admit. Look, the denominator, fine, 1 minus 1/2 is 1/2. The 1/2 here is no problem. The 1/2 raised to the power 11, that's actually a little bit painful. That would be 1 over 2048. You could do that on a calculator without any problem. It would be a lot easier than doing this if you had a calculator, right? You would just take 1/2 raised to the power of 11. So all this right here would be 1/2 minus 1 over 2048 divided by 1/2. Now the only unpleasant thing you'd have to do here is quite frankly, is this subtraction up here, which it is a little bit unpleasant, I have to admit. So 2048, you could use as a common denominator. So 1024, so that would be 1023 divided by 2048. How do you divide by a fraction? You flip and multiply, so by 2. So it's 1023 divided by 1024. Now, there's bad news, and the bad news is this is kind of maybe not all that. Well, look, it's easy, it's elementary. It's just add, subtract, divide, and multiply. I didn't use a calculator. It would really be no problem if you had a calculator. This still would be a royal pain if you had a calculator. This, you know, tappity tap, you get it done pretty quick. Hey, look at this top sum here. Imagine I went up to 100. I mean, I can't even imagine doing that with a calculator. But this, what would change on this if it went up to 100? This would be 101. Everything else would stay the same. And you could do 1/2 raised to the power of 101, and your calculator, there's no problem doing that. It would do that really, really quickly. So that's not a problem. Now, I already wrote the formula down. I kind of don't want to get rid of that formula right there. I said I'd keep these videos short, so I think I'll end this video here, but I need to tell you something, and that is the following. Let me erase this. This formula has some kind of interesting uses in biology, but looking at population growth and decay and stuff like that. But this formula right here, in and of itself, is not really the end goal. It's not really the thing we're looking for. We're going to use this formula right here. In fact, maybe I should write it down a little bit more neatly up here, and the next video will be all ready to go. So this is called the sum of the first n terms, and it's this sort of complicated looking, this sort of complicated looking term or thing or object here. But we're going to use this to get a formula that we really want, and that is really important, and that is really useful. So even though I'd like to go on to that right now, I'll keep this video, what are we at here? Under 15 minutes, okay. I said under 10, close call, under 15. This formula is going to morph into something really important. And here, you think about it. See if you can get it. What do you think this would be? Or what do you think this would mean? And I'll say no more about this. Think about this in the next video. This is what we want to get. And this is really important. So I'll stop right there.